let's talk about just like the mathematical topic of complex functions for a minute. And let me get rid of this. So a complex function f maps a subset of the complex plane to the complex plane. So this is an arrow. For some reason, the font doesn't come through. For instance, a complex function f can map a single complex number s naught to another. So s1 is another complex number that's equal to the function, complex function f evaluated at s naught. Just like real functions. How many of you have had a math class that has explicitly talked about complex functions? Yeah. It might have never, okay. You're a math minor, right? Yeah, that helps. Oh, you're a major. Oh, okay, double. Well, that's cool. Complex analysis. Yeah, so complex analysis is a great topic that I wish we had room for in the engineering curriculum. Everyone should just double major in math. No.
Everyone should just go to school for 15 years.
Yeah.
I'll dump all my literature electives for math. Yeah. I would do that.
I think a math minor if I didn't take history,
I'll drop all my engineering classes. Don't mock it.
history, philosophy.
I'm never going to think it would be a good thing for engineering school to get rid of the social sciences, natural sciences, well, obviously, and liberal arts and fine arts. Like those are all. I think that they're really key to becoming a well-rounded human being, to at least be exposed to that stuff. Yeah. Unfortunately, high school doesn't do a very good job of that either.
That's what homeschooling is for.
Yeah. So I know some of you are going to disagree with me on that point, and that's fine. Okay, so we're going to talk about a complex function, which, I mean, just like a real function takes in a real number and it gives you a real number, right? Complex function gives you a complex number, you know what those are, and it gives you a complex number back. So, not bad. And actually, I will give away one of the punchlines here. We've already been dealing with complex functions for a while. The transfer function is a complex function. Because S, the Laplace variable, is a complex variable. So, yeah, complex functions, you've been doing it all along. Didn't even know.
Just like a vector.
Yeah, so that actually we'll start interpreting it as a vector here. That's what I added today. So, a curve, so this is like a definition in a sort of an engineering sort of way. A curve in the complex plane is defined as a continuous function mapping the closed interval of the reals to the complex plane. Okay? So, if you come up here, we have a closed interval in the reals. So, closed means it includes the endpoints, right? And it maps to the complex plane. Okay? So, that is what a curve is. Now, there's a specific type of curve that we're going to consider. That is a contour, which is defined as a directed curve consisting of a finite set of directed smooth curves, the final endpoint of which is identical to the starting point. So figure A1 shows a contour. So it has to be made up of a finite number of smooth curves. So you could, if they're smooth, you could differentiate them, right? Smooth curves that end up at the same place that they started, and there's a direction to it. That's a contour. Okay? Notice that this function, gamma, it's a curve. It takes a real number and it turns it into a complex number. This is something that, have you guys ever done like a parametric plot before? That's what this is. A parametric plot would be the variable that your parameter variable, like t or whatever is commonly used as t. that is your real number that you're mapping to the complex plane. All right. So stuff that's like familiar but not maybe you've never explicitly been introduced to it. Sometimes we just like pretend like the math isn't there and do stuff, and that always scares me though. I feel like we should be okay with the math existing there. And so then we're going to talk about what we're going to do with this stuff. So a contour can be mapped by a complex function. So we could take this contour and we could map it with a complex function. It exists in the complex plane, right? So we could map the whole contour to the complex plane through some function that just changes it, right? Like we could squish it or we could stretch it or whatever we want to. We could do something to this contour. That's just what we'll do. The image of a contour mapped by a complex function f is itself a contour, okay? So f of gamma, as shown in figure A2. So if you take a contour and you run it through a complex function, you get out an image of the original contour, and it's also a contour, the new contour. And you know, I made it look recognizable, right? I sort of like stretched and shifted, and sometimes it does. Other times it doesn't look anything like the original did. But what we're saying is, if you can imagine picking a point off of this contour, f is saying where that point goes over here, and it tells you where each point goes. So not too bad. I mean, conceptually, it's pretty reasonable, I think. And don't worry, we're going to actually use this stuff, guys. This is not just for fun. Complex functions are of interest in control theory because transfer functions, one of the central mathematical objects of control theory, are complex functions. The utility of evaluating the mapping contours with complex functions arises especially in root locus design and frequency response design, especially for Nyquist stability criterion. So that's what we're about to talk about. We should have probably done this back when we did root locus, but we sort of glossed back then. Now we're getting real serious about it. So here's an example. Map the complex point s equals 1 plus j3 with the transfer function, which is a complex function. H of s equals s plus 4 over s minus 1. Sometimes we say that we are evaluating the transfer function at the point s equals 1 plus j3 when we do this. We might say it's evaluating. So what do we do? It is as easy as it seems.
Did we do this? We did.
Did we? We didn't do this, did we?
370?
Oh, in 370 we did. We may have talked about this. I don't know if we did this set of notes.
Yeah, could we just plug it back in?
Yeah, we just plug it in. I did talk about how to. I know I talked about how to interpret this stuff geometrically. I may have talked about this in 370. I doubt it though. Maybe I did, because in Bode plots in root locus we should have talked about it. So, in any case, all you do is you just plug in 1 plus j3 for s, right? Oop. And we have 1 plus j3 plus 4 in the numerator, 1 plus j3 minus 1 in the denominator, and the result is 5 plus j3 divided by j3, right? Does that look right? I mean, you guys probably know more than me on this. Does it look right? Does it seem right? Seems legit. And then we could, of course, rationalize and whatever. We know how to do that, right? So if we wanted to, we could multiply by the complex conjugate of the denominator, which is, we could just multiply it by j over j if we wanted to. That's going to give us a minus 3 in the denominator. In the numerator, that's going to give us negative 3. J times j is negative 3 plus j5. All of that divided by negative 3, which is equal to 1 minus j5 over 3, right? So that's just like good old-fashioned plug and chug. Thank you. It's like I have like an applause track. I should have that, right? I should just like hit a button and have the applause track, and then like the laugh track.
Would have gone good right there.
Yeah, it would have. Yeah, that would be clutch. I should do that. You know what I should do? Because I feel like you guys know me pretty well at this point, and you would expect something like that. I should roll in first day of class next year with the new junior crop because they don't really know me at all, and like roll in with like a laugh track queued up and all kinds of stuff, and just like totally deadpan the whole lecture. Like don't even mention the laugh track. Just like hit the laugh track multiple times throughout. Don't even smile. That would be great. Oh man, I have all summer to plan. Yeah. Yeah. Everybody was like freaked out and never went back.
Just make a soundboard with all of this stuff from different professors. So you can have like and then everybody just boom, 0. It would be so glorious. No one would get it, but it would be
Right. You guys would get it. That's what matters. All right. So that's, I mean, so that's complex functions, kind of in a nutshell, and contours and all that. But we're going to take a step further, and we're going to understand them from the sort of geometric point of view. And furthermore, we're going to do another example in which we actually map a contour, and we get a feel for that, what that looks like. Okay. You guys ever hear the term conformal mapping? You can say, I do a little conformal mapping.
Is that similar to the linear algebra doing the transformations and moving the shapes around?
It is analogous to that. Yeah. If you considered a linear algebraic object to be a map from the reals to the reals, well, actually, it wouldn't be the reals to reals typically. It would be some vector space to another vector space. If you considered the complex plane to be a vector space, then you could consider this to be algebraic. The complex plane, you could easily make into a vector space, yeah.
I don't think that's slides on the lecture notes.
It is not. That's why I sent around, I printed out I printed them out for you guys, because I edited this afternoon, so.
You guys want that?
Okay, so it is often helpful to interpret the complex mapping of a point or a contour geometrically. Let us consider a transfer function, h of s, with complex zeros, zi, complex poles, pj, and real scaling factor k. Okay? So every transfer function can be written as poles, zeros, and a scaling factor. Consider each factored term of the transfer function in terms of its magnitude and phase. We can write the magnitude of phase of the transfer function as follows. So we could say that the magnitude of the transfer function is equal to the magnitude of k times the product of the magnitudes of s minus each of the zeros and the product of, this is I, this is j, the product of the magnitudes of s minus each of the poles. That's the magnitude. And the phase we can write as being the sum, right, of all of the s minus zi's, and then minus the sum, this is j, of the angles of s minus the poles. So we're familiar with this from Bode plots, right? We've already thought in these terms in our discussion of Bode plots, and also in root locus when we talked about the gain and how to compute the gain and all that. So we've seen this a couple times now, but we haven't spent a lot of time thinking about it geometrically, although I did gloss on it. So let's consider the evaluation of this of these two equations at a specific complex value psi. Okay, so the differences psi minus zi and psi minus pi, which show up in all these terms, right? In all these products we have, if we plugged in s equals psi, which we're evaluating it at psi, we're going to have psi minus zi, psi minus pj, all of these psi minus zeros and poles show up in both of those equations. So those differences can be thought of as vectors in the complex plane with tails at zi and pi and heads at psi. Okay? So figure A3 shows what happens if we have a transfer function with specifically these poles, this 0, and this value of psi that we're evaluating at. So we just plopped it in, and this is what geometrically we could think of those differences as being. So this vector right here is psi minus z1, right? This vector right here is psi minus p1. And this one right here is psi minus p2. Okay. Cool. I mean, that's like a nice observation, but like, how is that helpful? Well, since we wrote these equations as being magnitudes and arguments or angles of these difference terms, we could think of them as being the lengths of these vectors that we just drew and angles of these vectors, right? So this is going to be the angle of psi minus z1. And the length of this, I'll call it out here, is going to be, well, I guess I could just do this, right? The magnitude of psi minus z1. There's the magnitude of psi minus p1, and then the angle associated with it is psi minus p1. So there's a sort of geometric thing, and the same would be true of p2. This is a geometric, vectory way of thinking about this. And it's going to be really helpful for us when we try to sketch our Nyquist plots. And in fact, the entire Nyquist plot is something that MATLAB can't draw very well. because there's stuff that happens at infinity that he doesn't really know how to represent very well. We can represent it in a sort of cartoonish way, and so we can do something that you can't necessarily plug it into MATLAB and see this result. We would have to interpret it in our way on paper. So this is it's going to be useful for us. All right, so this is one way to think of how a mapping is going to work then. We have a complex function, so let's just plug in, let's just say h of s was equal to it was s minus z1 divided by s minus p1 times s minus p2, right? That's our transfer function. It's our complex function. We plugged in psi, right? We stuck psi in that, and what we found is that the magnitude and phase of this, the magnitude of h of psi, is equal to the product of the magnitudes of psi minus z1, which is the length of this, right? Psi minus z1 divided by psi minus p1 times psi minus p2. Right? That is our magnitude, the image, the output of our function comes out to be this magnitude. And then the phase is similarly, but we sum and difference things. So we can get a pretty good feel then for how a contour, which is, you could think of as being comprised of a bunch of points, right? How a contour, the magnitudes and phases are going to change from these poles and zeros. And we could also start to imagine how, if we wanted to change how it works, we could drop in a pole here or a zero here, and we would be thinking about how that affects this mapping, okay? Okay, so I know it's a little bit tricky, but not too bad, and we're going to get a nice example now. Let I be the interval from 0 to 2 pi. Let the contour gamma be a map from this interval to the complex plane. Be defined parametrically, with t being an element of I. So t is something in that interval from 0 to 2 pi, as gamma of t equals sine t plus j cosine t. Does anybody know what that looks like in the complex plane? Circle. That's right. That's the parametric representation of a circle. So map gamma with the transfer function given here. This is also a slightly different example than the one that I had in the other notes. I tweaked it a little bit for fun. And plot the result. So what we're going to do is we could, of course, as we know, this is like essentially plug and chug, right? Like you plug in a point on this circle into this, and you evaluate where it is, and it comes out to be at a certain place, and you put the point there. You could do point by point and get the mapping. But what we're looking for is more of a feel, a geometric feel for where the poles are and where the zeros are, and how it affects how this contour gets mapped. Okay. And we can do that if we switch over to Mathematica, which had open, but is not open right now for some reason. Mathematica. All right, so this one. So, what I'm doing over here is defining the contour gamma and transfer function h. So, there are different ways to work with complex numbers in Mathematica. I'm choosing to I've found that working with them as just being a pair of numbers, just an array, it's easier. And just treating it like it's a vector the whole time is easier than actually using the imaginary number in there. So I give it the real part as sine of t, the imaginary part is cosine of t. And then my transfer function, I just plug that in. And I solve for and plot poles and zeros. So I set the numerator and the denominator of h of s equal to 0, and I solve for s, which gives me the poles and the zeros out. Real and imaginary parts I take there. And then I define the pole zero plot as this PZ plot, which I'm going to reuse.
That portion there, was that supposed to be on this page that we had the notes?
No, so what I do in the notes is I give you a simple script that you can copy and paste easily. Will do the full contour map, but it won't do all of the fancy stuff that I'm going to do. If you want that, though, you can click on that hyperlink and you can get the source code for the one I'm using in class. It just didn't look good in a figure because it's like really long, and most of it's just like formatting stuff. So yeah, I just simplified it and stuck it in there as a way of, like, if somebody wanted to just copy and paste like a quick and dirty example, they could see it. This is the other one's more minimalist. This one is more fun. So the next step is going to be to plot and animate gamma, and so gamma is the contour we're going to map with the transfer function, and h of gamma is going to be that mapped contour. So we're going to plot them both, and I'm going to animate them. So you can use parametric plot to do this plotting, and that's what I would recommend you use if you're using Mathematica. And I'm also going to plot lines from, whoops, it's running. Come on. There we go. I'm going to plot lines from the pole and the poles and the zero to the current point that we're plotting, the latest point that we're going to map. Okay, so if we're going to map this point, geometrically, we could think of there being a vector starting at each pole and each zero and going to the point that we're going to map, right? This point is on that unit circle that we're going to be mapping, right? That contour we're going to be mapping. So we have a magnitude here, which is the length of this is 1, right? It goes from -1 to 0, so the length of that is 1. The length of this is going to be, the length of it is, using Pythagorean theorem, this is 2, this is 1, so it's the square root of 5, right? Square root of 2 squared plus 1 squared, so square root of 5 is the hypotenuse of this, so that's that length. And then the length of this one, the 0 to the 1, is just 1, right? So we have 1, the 0, divided by 1, the first pole, times the square root of 5, which gives us 5 to the -1 half. And something that is definitely less than 1, right? And we see, so over here, I'm showing the image of what happens after you pass it through the function. You get this point here for that first point. The arrow direction is wonky just because I'm automatically generating the arrows. And this cyan color here is that that output vector that got mapped. So this has length of 1 over 1 times square root 5, and it has an angle which is the sum of these angles. So this one has angle 0, no contribution. This one has angle, what is that? Is that an easy angle? 2 over 1, rise over run? I don't know. I don't know that angle. Anyways, it's probably something reasonable. What would you call that? Like, it's like around 60 degrees, but it's not 60 degrees, right? Yeah. And then we've got a 90 degrees here. So this is a positive 90 degrees, right? Plus 90, because it's a 0. And then we've got 0 contribution there, and then we've got a minus 60-ish, right? And that gives us around 30 degrees. So that's why we get something that has a length of 1 over square root of 5 and an angle of around 30 degrees for that first point. And we're just going to watch it evolve. So as we move along the unit circle over here, we're seeing us move this direction here. So it means the magnitude is getting smaller, right? The magnitude is getting smaller. That means that the denominator is growing, right? Faster than the numerator is growing. The numerator isn't going to grow. The numerator is going to stay 1 always, because it's always this 1, 0, and it's going to go to the unit circle. So the numerator is always going to be 1 all the way around the circle, right? The denominator grew, though. So the denominator is growing, so we're shrinking, and then the angle, if you added up the angles, would be going to 0. They would start to cancel each other out. And when we get right here, pretty good. When we get right here, we have the angles perfectly canceling, because this is giving you a negative, call it 30 degrees, and this one's giving you a positive 30 degrees. And this one's giving you no angle contribution at all. And so you have 0 minus 30 plus 30. It gives you 0. And then we continue along, and down here, notice that it mapped symmetrically. And then we start to go way out here. Notice how much bigger the magnitude got. That's because we came pretty close to this pole here, and so that length wasn't very long. So that made it quite a bit smaller. Keep moving along here, and there's another situation where instead of adding up to 0 degrees, it adds up to 180 degrees angle contribution. And then keep going. It gives us this sort of, I think this is, I think they call those cardioids, right? Or they call them kidneys, because they look like that. Looks like a kidney. But I think it's a cardioid, though. Yeah.
It's just one point.
Because it just has what?
It just says 1 point.
Yeah. It's pretty cool. Cardioid. I like it. And so we've got our mapped contour. Started here and it ended there. Yeah.
What's the significance of the arrows, the orientation? Would you get the same solution if you went backwards?
So that is a good question. You would have, so the arrows go in a certain direction on this mapping, and they correspond to another direction on this mapping. And the direction is going to be significant for the contour, the interpretation of the contours that we're going to do for the Nyquist plot. You're right, it's the same shape, but the direction is significant in how we're going to interpret this. Yeah. So we'll see more on why that is. a little later on. But for now, suffice it to say that you are correct. Each point would still be mapping to the same point. The direction is only significant for noting. So, for instance, this is a clockwise encirclement of this 0 here. And that sort of thing will be significant in our Nyquist plots. The direction of the encirclements is going to be significant. Okay. All right, so that is the I don't know if it was really a review, but the tutorial, I guess, on complex functions and mapping contours with complex functions. Okay? So